I need to define a few more things and note some other relationships and theorems before I move on. Sorry, no examples in this video, just more sort of a potpourri of definitions and stuff. We already defined what expectation was for a function of a single random variable. It was an integral over all possible x, your random variable, where you put that function of x in with the integrand along with the PDF. Well, you could have a function of multiple random variables. You just have to take multiple integrals. It's a multiple integral for as many random variables as you have. But here it is. We'll put that in our back pocket for later use. If you just have two random variables, x and y, it's just going to look like this. So it's just a double integral. But you put that function in with the integrand, with the PDF. If that function is just the product of the two random variables, the expectation for the product of two random variables is this guy. More definitions here. We say x and y are uncorrelated if this statement is true. The expectation of the product is the product of the expectations. And we say x and y are orthogonal if this expectation of the product is just zero. So just defining those things now. Let's see. By the way, correlated is kind of like independent, but it's not as strong. Independent implies uncorrelated. Uncorrelated does not imply independent. Remember, independent meant joint PDF was the product of the individual PDFs, or the joint cumulative distribution function was the product of the individual distribution function. Covariance, another definition. What it means is this. This is the definition of covariance of two variables. Is this expectation? Subtract off their means and then take that product. Use linearity of expectation, you get this relationship. Covariance is this expectation of the product minus the product of their means. Here's the definition of the correlation coefficient. It's the covariance divided by this thing, which is the covariance divided by the product of the individual standard deviations. Or we can express the covariance as correlation coefficients, or correlation coefficient times the product of the individual standard deviations. And by the way, the correlation coefficient is always between -1 and 1. If the two variables are independent, then they are uncorrelated. Their covariance equals 0. The correlation coefficient equals 0. That is a one-way implication. Each can be true, and variables don't necessarily have to be independent. This latter one, you can read it, but it's not that important. Here's something neat I thought was neat about independence. We already knew this. If the joint PDF is just a product of the individual PDFs, then they're independent. And if they're independent, that's true. If and only if. Well, there's a theorem that says if the joint PDF is simply a product of functions that are individually just functions of the individual random variables, then they're also independent. The one-way implication is easy. If they're independent, then of course it breaks up into a product because it breaks up into a product of the PDFs. But if it breaks up into any kind of product that looks like this, then they're also independent. For a proof, see my notes. Here's an example. Let's say joint PDF is just the sum of X and Y, where each of X and Y are between 0 and 1. Well, you can't describe this as a function of X and Y individually. So they're not independent. You don't have to do any other tests. What about this guy? Here's the joint PDF. At first, it looks like, well, since it's just a constant, that maybe, you can express it this way. But you got to look at the limits. I mean, here's kind of what PDF looks like, or in the shaded region is where it's not 1, not 0, and outside this circle it is 0. So it's the limits can't be broken up this way because the limits are a function of each other in not a simple way, not a product type way. So these X's and Y's are not independent. Let's see. Expectation of a product of two random variables individually like this, a function of just one random variable or a function of just a random variable. If they are independent, the expectation of this product is the product of those expectations, those individual expectations. So like if X and Y are independent and you have this function, this expectation is this product of these individual expectations. Here's another example. Expectation of X squared, Y squared, if they are independent, is the product of the expectation of X squared times the expectation of Y squared. Good little tricks to know so you don't have to do other tests and calculations. One more definition. It's just a video of a bunch of definitions. Here's the PDF of the univariate Gaussian, also called the normal distribution. You've probably seen it before if you've had any probability at all. It turns out this mu is the mean. This sigma is, or this sigma squared is the variance. Those are a little bit hard to prove. I left them as exercises for my students. Here's a notation for that. This means X has the normal distribution, mean mu, and variance sigma squared. So if you see this n with, say, two numbers in here, the first number is the mean, the second number is the variance. The cumulative distribution function, it's this by definition, but there's no analytical form for that. You need either a table or a computer to find this. It's the good old bell-shaped curve, approximately 68% between plus and minus standard deviation, approximately 95% between plus and minus 2 standard deviations, and call it almost certain, or 99.7% between plus and minus 3 sigma. What are some good things about it? It's completely described by those two parameters, the mean and variance. The mean equals the median equals the mode. It's nice and centralized. It's symmetric about those things. It's a reasonable representation of many physical phenomena. It's commonly used. Distribution of a sum of non-Gaussians, as you make bigger and bigger sums or more sums of more and more things, will tend to a Gaussian distribution. The number of those random variables gets large. That relationship is called the central limit theorem, and it's kind of why it represents many physical phenomena, because there's many things going on in physical phenomena that sort of sum up to a Gaussian. And here's a nice one. Any linear operation on a Gaussian random variable is also Gaussian. I think that's enough. All the way back to 0. I think that's enough for this